Can you see my screen clearly now? Is it visible?
Yes, sir.
Okay.
Yes.
So let's talk about the challenges and solutions at the plasma water interface and also the plasma solid interface. So most of the ammonia synthesis is a gas solid reaction, but you can also make ammonia in the aqueous phase. So basically you have plasma interact with the water and then the generate plasma. So that's what we are talking about today. But we are also going to talk about plasma solid interface and how you monitor the solid surface the reaction and also what kind of the in situ the environment you may have. Let me ask you the question, if you just yes or no. Any, I know that yesterday someone mentioned you have a microwave in your laboratory. You are familiar with microwave plasma. So anybody has run the DBD cold plasma? Not that doesn't have to be catalyzed. Do you use the DBD for some other
Yes.
like the material synthesis? You can use the DBD for the material synthesis, and you can use the plasma for material synthesis. Doesn't have to
Yes.
be the reaction. Anybody have the cold plasma experience?
Yes, sir. We have cold plasma experiment.
Okay, cool. You do have cold. Okay, that's all right. I'm glad you have cold plasma. That's easy to talk now. So this graph I got from this the Science Advanced paper 2019. So I think I'm going to discuss this. I'm going to describe this for you, and then I want to have a discussion in the class about the scalability. What's the advantage? Just let's list some advantage and disadvantage. So what this does was, so DBD, we all know the DBD plasma, all right? So DBD plasma means, let me see. DBD, you basically you do need to put a catalyst in here. You put catalyst in here, and then you basically have something in the center, and then basically you have the voltage in here, all right? So you run the basically you connect to here, okay, and then between these two you have basically you put the voltage, it's high voltage, and then the plasma generated, all right? That's DBD. But this is not DBD. DBD is gas solid reaction. When you run the DBD, you need to have the nitrogen hydrogen going through this way. So the basic nitrogen going this way, ammonia formed, all right? So this is gas solid reaction, but this is not. Look at how they design it. Here's the description. They have the water phase in here. Then they have this is electron. This is non-catalytic. Okay, I'm gonna this papers. But it's non-catalytic, but they combine the electrochemical and the plasma. But the plasma is different from DBD. Do you see how where the plasma generated? And then this is the bottom graph is really enlarged or cut out. You see this plasma water surface. It's just a little bit water. Then they apply the voltage. They generate plasma. So now that plasma actually the react goes into the and so I think for and then basically it shows my internet is not stable. Can you hear me? Hello?
Yes, sir.
Can you hear clearly? Okay. Yeah, because some internet is not stable, but
Hello?
yeah. Can you hear me clearly? Is my
Yes, sir.
internet?
You are clear. You are clear, sir. You are audible.
Well, I'm going to start listing the pros and cons, advantage, disadvantage here. So let's see someone in the audience has experience working on the DBD. What's the advantage? And what's the so on this is the setup. What's the advantage and the disadvantage? Well, one of the advantage you can see. Did you realize there are no hydrogen? Which is good, all right. So I think that they didn't. I don't think they feed in the hydrogen. They feed in nitrogen. Hydrogen is generated from the water electrolysis, basically from the from water. So that is how this plasma interacted with the water and then form the hydride and then combine the hydrogen. But they do form the ammonia, not hydride. Continue. So this is very similar to chemical cell without plasma. Remember hydrogen evolution? They do have hydrogen evolution issue, but true, if you have the hydride, don't let hydrogen coming out, and then you can make ammonia. But the key is, I think this plasma here do some job because I think plasma come in, I think interact with the immediately with the nitrogen, and then they form some kind of nitrogen plasma that can react with hydride in the water phase. You follow me? Liquid phase. So anybody say no need for good things and no need for hydrogen, which is a saving. Anybody want to say any advantage, disadvantage?
Yes, sir. No, but by this method, sir, you are asking advantage or disadvantage?
Doesn't matter. You can say we can continue. So you can say advantage or disadvantage, whichever you can say. Yeah, I'm going to write it down. Go ahead.
Here, separate electrolysis is not required. Electrolysis process separately not required.
Is that one advantage?
Yeah. Yeah, it's advantage.
Electrolyte, all right?
No electrolyte.
No electrolyte. Yeah.
No electrolyte.
Yeah, basically no electrolyte. Yeah, that's good because conventionally, if you have the electrochemical reaction, you need electrolyte, and also you need a membrane in between. All right, but now looks like you don't need it, so which is good. So what else?
Then fossil resources like methane or hydrocarbon resources are not required for synthesizing hydrogen.
Thank you. Hydrocarbon is not needed. Okay, cool, good. Yep. Yes, I think that just if you think something else, just keep on talking. But I can see the disadvantage. Actually, I use some kind of the plasma cell like this. Okay, disadvantage is a need to maintain very close contact because this is the plasma jet, so cannot if you leave it too high, you are not going to have a reaction because this hydride electron will not happen because it's different from gas phase solid. So that means it needs to maintain the plasma jet close enough to the water. Yep, you have to because otherwise the water will you can't get those the water plasma species dissolved in the water and go into it. So it's you have very limited the space to move. So that's actually dictate the commercialization because commercial you can't have all the what you call all the jet close enough because if you build a large reactor, this water level also changes, all right? So if that gap is so critical, sooner or later your plasma will stop running. Okay, so that's the problem. Yeah. Anything else you can think of?
conversion of water into hydrogen is very minimum.
Yeah. Oh, talking about conversion.
Or else
So
peak
basically,
pressure also not found.
yeah. So basically, the yield of ammonia is very low. Yep. I can tell you. Typically, remember we talk about the in last section we talk about analytical. So you can use the GC and then you can use the mass spectral to analyze. Those are gas analyzer. You analyze right away. But here, ammonia is in liquid. You can't shoot the liquid into the GC, gas chromatograph, all right? So, and also concentration is so low. The GC, I think the good GC detection limit probably at the ppm level, but it's going to be the ppb level. So it's very slow until they build up concentration. Then you get one data point. Then continue build up takes probably hours and days. Then you take another data point. So I think that it's very difficult to scale up because where would nitrogen go? When nitrogen come in, they convert it to ammonia. Only a little bit of nitrogen convert to ammonia, and then the nitrogen will be gone. You are wasting the nitrogen. All right. So unless you run the batch mode, it's very slow. The kinetic is very slow. Yeah. So anybody think anything else?
There is some advantages. It can be low pressure. It requires only low pressure.
Yeah.
Low
Thank you. Yes. Low pressure. Yes. Low pressure, low voltage. Yep. So this different from DBD.
Voltage,
DBD you have yeah.
So actually voltage is high, sir. It's not low.
Oh, this voltage is high, but I thought they use DC. DC cannot be that high. You see that they use DC, all right? How high they can go?
Actually, dielectric barrier discharge is by through high voltage AC only, sir. So generated from high voltage AC.
Yeah. But this one I think they use the DC anyway. So yeah, I'm not familiar with how much voltage in here, but it looks like if you think it's high, that's okay. You're right.
Yeah.
This similar URI should be high. I think that's disadvantage, all right? There should be like DBD because otherwise it will not generate plasma. I think probably the voltage is even higher than the DBD because you are talking about the plasma. DBD is plasma between these two the electrodes, all right, in the center and also on the side. But this one basically depends on the electrode, how close you are to the water the surface. Yeah. So and also this one is I think it's a waste of a lot of nitrogen. I don't think this batch operation. Did you see the nitrogen coming in? They have a purge and the gas coming out. So if you conversion, I'm glad we did exercise on the calculating conversion. If conversion is low, I mean the data give to you, you have 5% ammonia, your conversion somewhere close to 10%. So if your conversion is very low, you need a lot of recycle. You better this nitrogen coming out, you have to recycle the back. Otherwise, you are wasted. Where nitrogen come from? Nitrogen is very expensive. They come from the cryogenic, all right? So I think this one has a lot of disadvantage of the nitrogen utilization. Yeah. So
yes.
Single pass, I would say single pass conversion is low.
Yeah, conversion is low.
Yeah, single pass conversion is low and requiring large recycle loop. All right, because 99.9% you have to recycle it, requiring large recycle loop. Yeah, that's the cost. Okay, good. I'm glad that we talk each other rather than listen to me list all the disadvantages you never remember. So it's come now. This advantage are coming from you. So
electrical point of view, electrical efficiency is very poor, sir.
You mean what's called electric efficiency, all right?
Yeah,
electrical efficiency.
Energy efficiency, yeah.
since you talk about electrical efficiency is very low, where is the electricity or energy wasted? As the thermal general heat, or is it just the disappeared?
Yeah, I will tell. No, sir. Actually, we are giving electricity. That electricity is converted into plasma. So
Yeah.
you calculate the intensity of plasma compared with input electricity. If you calculate the efficiency, then that conversion efficiency is very poor.
Very poor. Yeah. Okay.
For
So you're talking
DPT,
about,
particularly
you're talking
DPT.
about so you are talking about conversion efficiency. When you convert to plasma, that conversion is very low. Okay. Yeah. So basically, that electricity is really wasted, and then either as conductive loss or some kind of loss. Yeah. Okay. Yeah. I think this sounds pretty cool. But I look at this, it sounds pretty cool. Then I found out that in our university, we have similar setup. This is really for the, I would say, fundamental research. If you are really interested in plasma, but if you want to scale up and try to utilize, it's very difficult. Yeah. Okay. So, all right. Let's keep on going. Very good. So now this is basically the remember the topic today is challenge and solution at the plasma water interface. Now let's talk about plasma solid interface, which is the most popular because a lot of the gas solid interaction like methane activation, ammonia synthesis, and then some kind of the ammonia the decomposition cracking, they all happen at the plasma solid interface. So let's take a look at what happened on the solid interface. Okay. Yeah. So basically, this is really fundamental research. They have this is the non-thermal plasma. Obviously, that's the DBD, all right? So they have DBD and then the cat in the center. This is really a model. And then what they want to study is the reaction intermediate. That means when hydrogen and nitrogen adding together, what kind of intermediate form? I mean, what kind of intermediate is produced before they end up as ammonia? So basically, this is so-called in situ IPR to see the surface. Obviously, there will be NH on the surface and NH2 before they form NH3. All right. So there are a lot of the surface species. I would say surface species and hanging around in the surface. So this in situ IPR really powerful. They can really see what's happening. See they have the delta, the NHX and N2H, whatever you name. This IPR can see it and see the evolution of the formation mechanism of from N2 dissociate. N2 has to dissociate in order to combine with H. Is that right? So this in situ IPR really powerful. So okay. Any question on the tools here? How they do the study?
Thermal plasma can separate the oxygen.
Not.
I couldn't hear. I can't hear you. Can you repeat your question again? I cannot hear your question.
Thermal plasma can separate the oxygen produced from water.
Separate. Oh, so you are talking about previous one. You are talking about the oxygen separation, is that right? Are you talking about are you talking about this or you're talking about here? Previous. Oh yeah. Thank you. Yeah. So basically, in here that's why they have a purge. You see the purge here? They have to have a purge. Otherwise, you're right. The oxygen in the presence of oxygen, they are going to oxidize ammonia. You will not see ammonia. You will see NOx. Good question. Because in conventional electrochemical, they have this membrane in between. So then the oxygen will not come this way, all right? Oxygen will not come to hydrogen side. But now when you have here, oxygen will be the problem. I think that's the reason they use the purge. So make sure that the entire chamber is oxygen free. they had to purge very fast because the oxygen constantly is produced from water, is that right? The moment they form, they had to purge them out. It's a good question. Okay. And then we talk about in situ the measurement like this. So this in situ is very powerful. If you're familiar in situ FTR, they can track by the time they form the ammonia, how many steps they need to go through. So that's the in situ FTR analysis. So I think my lab we have both in situ Raman and in situ FTR. So that to do the this analysis, it helps you to understand reaction mechanism, so you can design either your reactor, your catalyst better. So in situ technique is pretty good, very useful. So take a look at this diagram. Give me the 30 seconds. I need to have water. My throat is very dry. I need to get some water to drink.
PPT. The color இருக்குல்ல gradient கொடுத்து என்னங்க இல்ல நான் ஒண்ணும் பேசல, அவர் அந்த பிபிடி எப்படி போடுறதுன்னு தான் கேட்டாரு.
Okay, so it's basically this the picture shows how you run the so-called gas solid the plasma. It's from my student paper. So her name is Sarojini Tiwari. So she did a fantastic job to design different scenario of the microplasma. On the left hand side, the picture A shows it's just the plasma. Okay, microwave cavity, you generate spark, and then you put any molecule in there, you run reaction. Let's say the thesis is really run the methane and nitrogen all together to make ammonia without using hydrogen. But I think yesterday someone asked me a question, how you generate plasma at ambient pressure. Well, you see what she did, all right? You follow argon first, and when argon come in January, slowly back out the argon, then have a methane and nitrogen come in. And then you can see this pink color is the nitrogen, and then methane is like a light blue color. But because of the pink, the majority of the plasma actually from the nitrogen. So then reaction started. I asked you yesterday or 2 days ago if you observe plasma. There's the instrument called the optical emission spectrometer. You can see the plasma, which is very important. When we get on the picture C, you will know, you will understand why. So can anyone tell me if you have ever used the optical emission spectrometer just to see the plasma in the plasma zone?
We had about optical emission spectrometer, sir, but in our laboratory we don't have.
Okay.
We are not having experience with that. Yeah.
It's very important. If you do the catalysis or the material science or the having the plasma interact with your material, you need to buy one. I will tell you why. So let me jump to on B from A to C. It's the no catalyst. Here's the catalyst. Run the microwave plasma catalysis. Either you put catalyst inside the cavity, But the trouble is because it's so hot, then sometimes the cat has got damaged. Most of the time we put catalyst at the edge of plasma, so-called afterglow. So the challenge will be you have to make sure you are plasma catalysis, not the just conventional. The reason being that when plasma coming after the end of the zone, they kind of try to find the electron or something disappear. So that means they could capture some other molecule disappear. So your job is to put this the optical emission spectrum on the surface, make sure the incoming species is plasma. Then you are talking about the plasma chemistry. Follow me? Otherwise, you are talking about conventional. Remember, I keep on reminding you let me see. I'm not gonna draw. Okay, remember, I keep on reminding you about the activation energy.
Yes.
It looks like, yeah. So basically, let me draw very quick. I don't want to go to annotation because I may not be able to come back somehow. So you remember this, and then we have. I'm trying to find a better way to do this.
Yes, sir.
Okay, so basically you have this across the mountain also, and then the plasma is. I'm sorry, I'm going to just describe. So remember you have to across the activation energy, but if you have plasma, your starting material energy is high, so that means the energy barrier, the hill, is not very high because you already started. Just for the sake of argument, if you compete with someone and then say, let's see who can reach the top of hill faster. Your friend starting from the bottom of the mountain edge, you basically have a helicopter lift you to halfway on the mountain. Of course, you are faster, is that right? Because that helicopter is a plasma generator. You follow me? So this is a similar analogy. If you compete with somebody, you better start same on the ground and then you climb together. Is that right? So see who can be there. But what if you have a helicopter and then give a jump start? So that's plasma. So, but the key is you have to know if indeed you get lifted. That means if plasma and reach the surface. Sometimes plasma die the halfway. You even don't know. So it's very important. That's why I mentioned the other day. So you need to have the optical. It's called the OES, optical emission spectrum. It's not expensive. You can buy it. You can buy it easily. But we found out it's very important for plasma, microwave plasma direction. In the middle is our baseline. Basically, this is just the the no microwave, no microwave plasma. We want to compare this scenario, plasma but no catalyst, plasma with catalyst. Here, no plasma but with catalyst. So this is going to be baseline. Two scenarios we need to compare with and see how good the plasma is going to be. Okay. So, any questions until this point?
Yes, sir. One question, sir, about measuring the plasma.
Yeah.
You said for doing plasma related or plasma catalysis related research, so you must need optical emission spectrometer. So in that, can you give some guidelines to get that instrument in correct manner for our research?
I can email Dr. Anand. Not only you need an instrument, you see this spectrum, you need a software. You need a software to interpret these peaks. See my student label peak, that software will actually interpret. So the instrument I bought, I think cost me, I forgot, $80,000 or no, not 80,000. I'm sorry, $13,000. It's not that expensive, but the software cost me $8,000 because you need a software to interpret the species. Otherwise, see my student already label this, okay, and then without software, oh, you don't have peaks. Then you say, oh yeah, I have plasma. So what? You don't know which one is which plasma. But by having the software can calibrate for you and then tell you. So I can send you the model and then the manufacturer where I will send Dr. Anand, and then yes, who we buy. Okay, so yep. So basically, I think I oversimplified it. You need this, and then you need a software to interpret it. Okay, it's more like a GC mass spec. You heard about GC mass spec, all right? It's a gas chromatograph compared to mass spec. So you need a library. So which means GC will separate the species, but the mass spec will identify the molecular weight, and then you need a database, and that database costs you a lot of money. And also, you cannot trust the database because sometimes database they are sent wrong they basically pick up the wrong data. So the human being has to sit in there to see, oh, if based on this the so-called spectral, if what the software says makes sense. Okay, thank you. Very good question.
Yes, sir. One more thing, sir. See, in a single, you said that software package or the library package.
Yeah.
So in a single library package, we may predict all precursor or all radicals which will come from plasma.
You have to do your own analysis. You cannot simply trust you cannot just trust the library. So for example, it's same as the mass spectrometer. When you see the molecular weight, it may not be the so-called mother peak. They could be the fragment, right? So you have to make a judgment if they pick the correct molecular weight or they miss that molecular weight. The same thing with the plasma species. That the software will tell you which one is which one the species, but you still have to make your own judgment. For example, this one is the methane. We published it already. It's the methane plus nitrogen give you the ethylene and ammonia. Do you see the how many clicks in here? My students spend a lot because we know for sure there's the ethylene C2. So for a long time, my students found oh, this is C2. She thought that was ammonia, but it's not. Okay, so that's why you have to really be careful. When you cannot just simply trust the software. So you have to make your own judgment. Okay.
So we have to buy with the range of molecular weight, sir.
Yeah. Oh yeah. Oh yes. You're right. You have to, because the same as mass spec. I'm pretty sure this is the OES is dealing with the gas phase. So if you buy the whatever the software that is dealing with the light molecule, it should be fine. Don't buy those for like the what you call that liquid, because your plasma will not the OES will not see those liquid drop. They will only see the plasma species. It has to be in the gas phase. That means the molecule will be very small. Typically, you will know methane, ethane, and ammonia, whatever you name. Those are the small molecules. Yeah, CO2, you will see it. Yeah. Okay.
One more question.
Go ahead.
Sir,
Go ahead. What's the question? Yeah.
Plasma, you have to supply water at room temperature, or else we can increase the water temperature and boiling point for better efficiency.
Very good question. So now you are talking about this one, all right? So you say that the water temperature will affect the plasma formation. Is that correct?
Yeah. If we increase the water temperature, the efficiency of the plasma increases.
Yes, that's of course, yes. So that's good. That's very good. So that's very typical. Typically, something similar like this in a commercial place, but this has not been commercialized. They basically do the heat changing. They basically send heat, and then basically you have heat changer basically deep into the water, and then whatever waste the heat coming out from other unit, you heat it up. Yes, it's going to be more efficient if you heat up the water to a certain temperature. But you don't want the water to become boiling, because you have steam coming out. It's an open system, because the nitrogen come in, and then the purge gas come in and purge out. So you probably can heat this to 80, 90 degrees C. Don't let it, even that you vapor the steam vapor will come out. But yeah, but good approach. So okay. Now I'm going to use the any more questions? Yeah, all those are very good questions. So you see there's several scenarios you can run plasma only, and then the plasma the catalysis, but catalysis put in the afterglow or the post plasma. So since we are talking about this, I'm going to show you a cartoon there. There's some terminology. If you open the literature, it's called in plasma catalysis. That's DBD. And then there's some post plasma catalysis. That means you have to get the plasma to begin with. So that basically elevates the molecular kinetics or energy. So it's easy to cross that energy hurdle. But the key is you have to keep a gap, the close gap between this and the catalyst. Otherwise, you know, the catalyst will not be active, or will not see the plasma. It's only see the hot gas. Okay, so yeah, so there are the two different scenarios. If you read literature, keep on using the keywords back and forth in plasma, post plasma, but in plasma just think about DBD is in plasma. Okay, all right. So talk about the plasma in the gas phase and gas solid phase. So there are different tools you can utilize to measure. So this is a tool we developed with the other universities. So what's happening was you need to have OES to see the plasma, make sure, and then you want to use the microwave to generate plasma, then floating through here. The difference is we are doing this on daily basis. Microwave generate plasma to begin with, but the catalyst you are putting here, and then we use the OES to observe, make sure it is plasma landed. Now once that thing happens, then we use in situ IPR to see what species react on the catalyst surface. This in situ IPR is very very powerful because we have OES spectra, then we have in situ IPR spectra. So we combine them. This spectra shows the species in here, and then this spectra shows those species anchored or right on the surface. So by combining this spectra, you will have a lot of the reaction mechanism information. Okay, make sense? Anybody have any questions? So that's a lot of in situ the tool we built at West Virginia University. We just built a Raman. We already have in situ IR. Then we will have some kind of other in situ measurement. We also team up with the national lab, have the in situ what you call in situ exact, basically see the bond under the microwave. All right, so I think I just have a couple more slides. Then I think we can talk about if any question I can answer. But let me show you. This is all we published the paper. Everybody is just wondering, that when you have nitrogen, hydrogen come into a chamber, what is going to not nitrogen? You have nitrogen, methane come in. I mean, some people say, oh, they all carry positive charge, but not necessarily, because if they carry all the positive charge, where would the negative charge? You can say, oh, negative charge is electron. Yeah, but that's still subject to debating. But this model we build is just assume you kick out electron, and all the remaining species is short of electron. Okay, we say it's fine, and then let's see on the surface positive charge. But even if we say this, we still don't believe all the species come in carry positive charge. Then where would the electron go? All right, electron has to be die somewhere. So anyway, so this is what we built, and then we found out when we have just plasma on and plasma off, then the selectivity this on relative basis or isolation is very high on plasma on. So plasma does do something, and in terms of the activating the what you call the methane molecule. That's otherwise you will not see the ethylene, right? Okay, all right. Anybody have any questions so far? All right. So this may be the could be okay. Go ahead.
Sir, in your laboratory, you are having optical emission spectroscopy. You're using that for evaluating the energy efficiency, especially how electrical energies get converted into. You are using microwave, so microwave to microwave used as a plasma creator.
Yeah.
So what about that conversion efficiency? How you are evaluating, sir?
Okay. So basically, thank you for the question. This question has been asked every conference we went to. First, your laboratory equipment doesn't matter your thermal furnace or your microwave generator are not built for efficiency measurement, which means you have so much energy loss. The laboratory reactor we build, okay, it's just to make sure we focus energy in the cavity, we focus energy on the catalyst, and here we also focus on here. But it's not optimized. Only when you go to commercial, people must start more optimized. Now, to measure energy efficiency, there's no way you can measure how much microwave power end up on the molecule or the because during the microwave transmission and during the microwave plasma generation, there's so much energy loss. I mean, even power electronics, all right, not power. Yeah. So you have loss, all right. So because when you plug your generator on the wall, and then whatever the energy coming on microwave energy, you lost 10% or 20% already, all right? So there's no way you can measure. Yeah, but when you go to commercial, there's a different way to design it. So which means I know what you want. You basically think that okay, you to ionize the species takes so much energy, all right? Let's say you have a handful molecule. You ionize, you can calculate the what you call the ionization energy, all right? For example, I can tell you N2 that you need 15 EV to to ionize the N2. So your question is, by adding those together, we know the ionization energy, how much that compared to the energy input from the microwave. In laboratory, it's very difficult to measure because those numbers are bogus number because a lot of energy wasted to the environment. Did I answer your question?
Yeah, yes, sir. I understand, sir.
So even give you a good example, okay? So I used to work, I worked half of my career working in the industry, just steam reforming. In Heber-Bosch, Heber-Bosch plant, remember, half of capital on steam reforming. I run steam reforming in my laboratory. How do you run steam reforming? So you basically, very good question. That's why we need to talk. So you have the fixed bed reactor, and then what you need to do is you have the, I would say, it's called resistive. Okay. This symbol represents the furnace. So basically, it's called resistive heating. I mean, heat transfer this way. Essentially, you basically what we do in a laboratory conventional heating. We have a furnace, and then having the ceramic, the insulation, the heating mantle in there. Then you have this what you call that electric wire, all right, so-called resistive heating. Then the heat radiate into it. So this type of furnace for steam reforming if you want to measure efficiency, it's difficult because for the whole body mass, they basically the heat are wasted. Industry doesn't do this way. Industry basically just do the combustion. Keep in mind, combustion efficiency is 80% by itself. They combust, and then basically they radiate, and then what you call that, convectively just heat the reactor tube, steam reformer tube. So then that become very efficient. It's convective heating. But in laboratory, it's all conductive. You can't do that. So laboratory reactor is not optimized. There's no way you can measure. So in the conference, everyone says, oh, you can measure. See how much you furnace the energy, how much you reaction activation. No, it never be the efficient. Okay, so it's a good question. Yeah, I'm glad that today there are a lot of questions today. So that help me to have some idea on what's the audience, the knowledge. Otherwise, sometimes I go to very basic, which you already know, or sometimes I stay too high level, you get a lot. So keep on asking questions, then based on feedback, I know how I'm going to control the speed of my lecture. I know how deep I need to interpret each of the slide. Okay. Any questions?
Sir, one more question from plasma solid interface, sir.
Plasma and what? Plasma solid interface. Go ahead. What's the question?
Actually, we usually have metal hydrates as one of the hydrogen storage element.
Yeah, metal hydride. Is it metal hydride? All right.
Yeah, metal hydrates.
Okay.
Yeah. We can take hydrogen from metal hydrates.
Yeah.
Is plasma will helpful for that or?
Yes, we did that. Basically, the plasma is going to
chemical looping.
Yeah. So that's the chemical looping approach. So next week I'm going to spend maybe I will do 1 or 2 lectures on chemical looping. That's the chemical looping approach. Okay. So I'm glad we still have time to talk. So chemical looping approach. Remember, for ammonia synthesis, you can have. Actually, we have a paper published. You can have Mn, M is metal, and then make a nitride. React with H2, okay, form ammonia. You can also have MH react with N2, because this H interacts with the M at a certain temperature. They are very reactive. This MH, that H, at a certain temperature, when you release it, it's more reactive than H2. You follow me? Because it's atomic. H2, basically, you have to dissociate in order to react with the N2, all right? Here, you don't need to dissociate. The moment you heat it up, they basically either go hydride coming out, and then we attack the N2. Yeah, that's a very good approach. Yeah. And also, I think I like probably sometimes too much the information. I did a lecture on the day when we talk about different methods of making ammonia. So you can do even more fancy. You can have MNH, that means metal, nitride, hydride. And then this one just reacted instantaneously. Yeah. Okay, good question. Yeah. Anybody have any more questions?
Any questions? Yes, sir.
Go ahead.
No question.
No question. So I think I don't know if Dr. Anand is in the classroom. Say it again. Yeah, MNH means M represent the metal. I mean this complex, okay, and the N means nitride, hydride. There's a Japanese group did this. Basically, they build nitride, hydride in one assembly. I had one slide on second day. I think I talked about it. Probably you didn't catch what I say. Yeah, the Japanese make this one, and then it's still chemical looping approach because they had to rebuild this material. Yeah, you can have nitride, you can have hydride, and then you can have the nitride hydride all together because that's all chemical looping approach. This way you break equilibrium. Otherwise, you have N2 H2 together in the vessel, they are going to subject to the equilibrium. So yeah, okay. So the next week, so today is three sessions. Yesterday was 3 sessions. Next week, according to this schedule, on day 8 and day 9, there'll be 3 sessions. So I'm gonna change them. I cannot. I mean, I think you guys know the time that it's 5:30 in the morning. I start from midnight. So last 5 days I didn't sleep. I only sleep a couple hours during the day. That's all. So it made me so tired. I cannot keep on talking for 3 hours. So when we have this, I need to talk to Dr. Anand. On day 8 and the day 9, when we have 3 sessions, and then one session we will do homework exercise. I will give you a problem, just like today. You got to do a calculation. I will give you different problem solving or problem learning rather than I keep on talking because it's midnight here. It's very difficult to keep straight 5 hours because you guys go to lunch and the break. Essentially, I have to stay awake for 5 hours, starting from 1 a.m. to 5:30 a.m. So it's really make me so tired because I have day job. At 8 o'clock or 9 o'clock, I start working. So yeah, okay.
Yes, sir.
All right.
It's very challenging.
It's very challenging because
planning.
this is yeah. I don't know who designed this courses from the university. I don't think Dr. Anand designed it. Someone, how can you teach like 10 days and each day you have like a straight like whole day? I mean, what do you learn? I'm pretty sure a lot of things going through your brain, you forget about it. So that's I mean, learning is you learn, you digest, you learn and digest. But I think last 5 days, I don't know if you guys can digest. I mean, so I can keep on talking, but if if you don't learn, it waste your time, waste my time. So that's why next week, for the 3 session days, I'm one session in the middle. I'm gonna give you some either homework or some kind of exercise. You do either calculation, and also we will definitely follow the topic. I'm gonna talk about technical economics. It look at that interesting, and also the chemical looping. That's also interesting. As for the other one, hydrogen fuel cell efficiency, I probably will go quickly because hydrogen fuel cell it has nothing to do with the ammonia because it's hydrogen fuel cell. I don't know why this topic is in here. I'm going to change a couple of topics and also life cycle. No, life cycle is not for me. And also future trends in sustainable ammonia. We talk about so many ways to make the ammonia: electrochemical, plasma, chemical looping, hydride, metal hydride. These are the future, is that right? So that section, future trends in sustainable ammonia, we already talked about it in the last 5 days. So I'm going to change these 2 topics: future trends in ammonia, since we already discussed, and also the problem solving on hydrogen fuel cell. I'm not a fuel cell guy, but I'm going to change to the different topic. And then because I want to show a lecture, these 2 sessions, I'm going to lecture not plasma, microwave catalysis for the plastic upcycling. I'm sure you'll be interested. Plastic upcycling means you turn polymer into monomer. Then you basically go to circular economy. We have huge program doing that. So you will see how microwave, that's not going to be ammonia anymore. It's going to be a microwave applied to plastic, upcycling, and then turn that into the monomer. How the catalyst doing that. The other one is basically hydrogen product, clean hydrogen. So that's associated with ammonia because green ammonia, you need a green hydrogen, but it doesn't have to be green. You can have clean hydrogen. Clean hydrogen means there's no hydrogen, no CO2 to come with. Let's say methane pyrolysis and also plastic pyrolysis. the whole process doesn't produce CO2 because the carbon went into the carbon nanotube. So I'm gonna probably change the two topics, and then I'm pretty sure you will like it because we present this around the world. Everyone say, yeah, that's the way to go. Yeah. Okay. All right.
Yes, sir. We can plan accordingly, sir. And
Yeah,
sincere apologies for the trouble, sir. Past 1 week, we are disturbing you in mid.
Oh, no problem, because I promised doctor, I promised you, we are going to, I'm going to do this a year ago. I don't want to change it, but I didn't realize it's 10 days. I have to lecture 24 sessions. That's too much for me, but it's okay. We are halfway through. Yeah.
Yeah, initially we planned offline basis, sir. So that's why the schedule at all we have planned. We expect you. We will present in India and we will meet directly. But unfortunate situation,
I can't travel to India. The reason being that I'm teaching courses. During the day, let's say that during the day I'm teaching. During the day, and then now I teach during the night. In the meantime, I have a large research group, so I have to do a lot of research. Actually, my main focus is research. Teaching is my side job. So I do teach in the fourth semester. Is an unconventional catalysis, and then now I'm teaching you guys during the night. So it's okay. There's 1 more week to go because So we will see.
Yeah.
But the only thing that's a 2-3 session day. I'm gonna change one session to the homework or I would say the practice in the classroom. Be prepared. You may need to have some calculation or some kind of brainstorming. I will give you some kind of condition, and you brainstorming, and then just like today you did calculation. It sounds very simple. That calculation, I don't think anybody make it correct. Yeah. So
yeah, sure, sir. That also very much useful to us. You can give the work we will do, sir. We can plan accordingly, sir.
Yeah, yep. So let's do that. Let's do that next week, okay? But next week I will change the 2 sessions. Instead of talking about ammonia, I'm going to talk about the low carbon footprint hydrogen, which is methane pyrolysis, and also the plastic pyrolysis altogether. The other is the plastic upcycling, meaning so that's all use microwave and microwave plasma. So that's because ammonia topic we spend like 5 days already. So next week we spend another 5 days. We beat a dead horse already. So that's why I'm gonna cancel this. Not cancel, change the future trend in sustainable ammonia because we already talked already. The other the hydrogen fuel cell. I don't know why hydrogen fuel cell. The fuel cell is a completely different animal. So yeah, it has nothing to do with the plasma or microwave. Yeah, it's okay. So but I'm gonna switching to the relevant topic on the microwave. Okay.
We can alter it, sir. Yeah, we can alter it, sir.
Sure.
Thanks for your endless effort, sir. Yeah.
Okay.
Thank you, sir.
Thank you. Have a good weekend. I will see you on Monday. Okay. Thank you. And Dr. Anand will send me the Monday the link. Now, right? So.
Sure, sir. We will meet on Monday. Happy weekend. Happy days.
Okay. Happy. Yeah. Okay. Good.
Wake up.